What does this engine and this person have in common? That's right, both have to breathe in order to function. People and engines function better when they breathe better. That's why we use turbochargers on engines, and that's what we're going to discuss. Operation of the diesel engine is based on the following simple principle. Fuel plus oxygen yields power and combustion products. And since it takes about 15,000 gallons of air to burn 1 gallon of diesel fuel, it is very important that the engine receive plenty of air. Turbocharging an engine, as we'll see, enhances that supply of air, which improves engine performance. The idea of turbocharging is not new. Bushey first conceived the idea in the early 1900s. Bushey reasoned that if he forced more air into the engine, the efficiency of the combustion process would be increased. Consequently, the engine would burn cleaner, since there would be fewer unburned hydrocarbons left over from the combustion. Bushey's simple scheme of using exhaust gases to compress the incoming air is still in use today. What he lacked was the technology to develop materials which could withstand the high operating temperatures and speeds required in a turbocharger. Bushey's idea went undeveloped until World War II, when the aircraft industry brought turbocharging to a reality. At high elevations, there is less air pressure, and therefore less density than at sea level. As aircraft began flying higher, it became increasingly difficult for engines to receive enough air for efficient combustion, so compressing the intake air was required. Since Bushey's time, metallurgical advances have been made, and out of the need for compressed intake air, turbocharging was born. In the 1950s, Caterpillar introduced its first turbocharger. We've made progress in turbocharging since this first 150-pounder, but the basic principle is still the same. Increase the flow of intake air for better combustion and engine efficiency. Even though it seems like we get a great deal of power from the combustion of fuel in our cylinders, it turns out that a great deal of heat energy goes to waste. About 10% is lost to heat transferred through the oil, another 30% through the radiator, and still another 30% through the exhaust stack. Turbocharging uses some of this last 30% to compress the air entering the intake manifold. Let's take a look at how this is done. This slide illustrates the flow of air in our system. Starting with the air filtering system, air is sucked into the turbocharger, compressed, forced through the intake manifold, and then into the cylinder where combustion takes place. Exhaust gases from combustion rush out through the exhaust manifold and are directed onto the turbine wheel blades. The turbine and compressor wheels are mounted on a common shaft and therefore turn together. This common rotation continually forces air through the intake manifold and then into the cylinders, starting another combustion cycle. The result is increased engine horsepower and torque, as well as cleaner, more efficient engine operation. The turbocharging process is carried one step further by aftercooling the compressed air. An aftercooler allows the hot, compressed air to flow around tubes that carry water, similar to a radiator. Heat from the air is transferred to the water, reducing the temperature of the air. Air gets more dense as its temperature drops. Therefore, aftercooling allows us to pack still more air into the cylinder without damaging engine components from excessive heat. Aftercooling also reduces exhaust temperatures, which extends piston, ring, and exhaust valve life. Now let's look at a turbocharger piece by piece. This will give us an opportunity to discuss each component's function and design requirements as well as features and benefits. We'll also see how each component relates to the complete turbocharger assembly. The first component we'll look at is the turbine wheel and shaft. This starts out as two separate pieces and is joined together by inertia welding, a precision, high-strength welding technique. The turbine wheel is cast from a nickel-base alloy, which can withstand the 1100 to 1400 degree Fahrenheit operating temperatures that exist in the turbine housing. Casting is carefully controlled to assure that the wheel does not contain structural defects which could alter its balance or strength. Since the wheel rotates at 100,000 RPM or more, any weakness or imbalance can cause turbo failure. Competitive replacement blades, as we'll see, can be thinner and or unbalanced when compared to Caterpillar wheel and shafts. Using parts which don't conform to CAT specs can lead to early failure. The function of the turbine wheel is to accept outgoing exhaust gases, therefore causing the wheel and shaft to rotate. Another one of the shaft's purposes is to provide a means to which we can attach the compressor wheel, which is our next component. The compressor wheel is retained on the shaft end opposite the turbine wheel by a nut and is made of cast aluminum. Its function is to force incoming air through the intake manifold or aftercooler. Unlike the turbine wheel, the compressor wheel is not subjected to high exhaust temperatures and need not be made from heat-resistant alloys. Balance and structural integrity are important, and the wheel's manufacture is closely checked with a fluorescent penetrant and X-ray techniques to detect defects. Again, competitive replacement parts may not know our wheel balance or structural requirements. Just because competitive parts may look like Caterpillar originals doesn't mean they'll perform like Caterpillar originals. The next component in building our turbocharger holds the turbine and compressor wheels and shaft in place. This component is the center housing. It is the foundation which all other turbocharger components either attach to or are contained within. In addition, it houses the lubrication system that is vital to turbocharger operation. We'll look at two lubrication systems in a moment, but first, let's look at the two types of bearings used to support the shaft inside the center housing. Technically, these shaft bearings are called hydrodynamic full free-floating bearings. They are unlike engine bearings, such as crankshaft bearings, in that they are not fixed in a seat, but rather float freely on a film of oil. Not only can the shaft turn within the bearings, but the bearings are also free to rotate relative to the center housing. Research has shown that during operation, these bearings are turning at about 30% of the wheel and shaft speed. Without this design, bearing failure could be imminent. Turbo bearings are made of either bronze or aluminum. These bearings are made of nickel-coated bronze. Note the oil passage holes drilled in the bearing. Much like engine crankshafts, the center shaft of a turbocharger is subject to axial or thrust loading. Exhaust pressure on the turbine wheel and boost pressures on the compressor wheel cause thrust loads to be transmitted along the shaft. These loads are counteracted by the thrust plate and bearing. Without the thrust plate and bearing, the axial movement would cause the blades to strike the housings, destroying the turbocharger. As we mentioned before, the center housing contains the lubrication system as well as the bearings. Caterpillar uses two different lubrication systems in its turbochargers. These lubrication systems are vital to turbocharger operation. Since the shaft rotates at 100,000 RPM or more, loss of lubricant can destroy a turbo in as little as 5 seconds. One lubrication system has a main center passage which allows lubricant, shown in red, to flood the bearing bore. A channel coming off the main center passage supplies the thrust bearing with oil. The second system has a main channel which feeds individual passages. Two of the passages go to the shaft bearings while another lubricates the thrust bearing. Oil entering either turbocharger oil system is in its normal liquid state. But after being exposed to high temperatures, the oil can thicken to a tar-like state. This is called coking. For this reason, oil drainage is critical. In addition, each time an engine is shut down, a 5-minute cool-down period is important to turbo oil system life. Without cool-down, the tar-like oil can bake inside the housing, eventually turning to solid carbon. This can result in severely restricted or plugged oil drains. Once this occurs, the lubricating, cleaning, and cooling functions of the oil are impaired, and internal damage can result. Resulting oil pressure buildup can cause failure. The next component required on a turbocharger is the heat shroud. It is a one-piece stainless steel or ductile cast iron component that fits on the shaft between the turbine wheel and the center housing. Its function is to slow down heat transfer from the turbine end to the bearing area. This is accomplished by creating a dead air space adjacent to the bearing housing. Since still air transfers heat at a much slower rate than metal, the passage of heat from the turbine end is greatly reduced. If the heat transfer were not restricted, lubrication breakdown, increased coking, carbon buildup, and reduced bearing life would occur. Shown here is the seal ring used to keep oil in and exhaust gases out of the center housing. This ring has a spring action similar to a piston ring. It springs out against the bore, which holds the ring in place. Many of our competitors use a cast iron seal ring. Caterpillar uses a chrome alloy seal ring for better heat-resisting qualities. This material also reduces seal ring spring loss. Caterpillar sets the chrome alloy seal ring in a step bore, which allows extended seal and shaft life. If this ring were set in a straight bore, compressor air pressure or exhaust gas pressure would force the ring hard against the groove, causing severe wear on the shaft. Our step bore holds the seal ring firmly in place, eliminating excessive oil consumption. While competition often skips this extra machining step and may use a common cast iron seal ring, Caterpillar feels the chrome alloy ring and step bore are necessary to give the service life our engine users expect. Turbochargers also require two housings to contain the turbine and compressor wheels. The first is the cast aluminum compressor housing, which fits around the compressor wheel and attaches to the center housing. Its function is to convert the velocity energy of the air to pressure and direct that air to the intake manifold or aftercooler. The second housing is the turbine housing, whose job is to collect and direct exhaust gases coming from the engine. In order to provide strength and to resist high temperatures, the turbine housing is made of special high-strength, high-temperature resistant cast iron. The last major component of the turbocharger is called the nozzle and can be found inside the turbine housing. Most nozzles are a part of the turbine housing casting. The function of the nozzle ring is to direct exhaust gases to the turbine wheel blades. It is critical that the turbine housing and nozzle are properly matched. A nozzle that is too large, with too much gas flow passage area, slows the rate of airflow to the engine, causing it to run excessively hot. A nozzle that is too small, with too little gas flow passage area, causes pressure to increase in the turbocharger. Improper nozzle size can cause engine component life reduction or failure due to excessive temperature or pressure. Competitors do not know Caterpillar engine or turbo operating requirements and may mismatch the nozzle rings and turbocharger. This can lead to turbo or even engine failure. Now that we've built a complete turbocharger, let's review the components. Wheel and shaft compressor wheel, center housing, bearings, shaft and thrust, lubrication system, heat shroud, seal ring step bore, housings, and nozzle. Let's next look at another turbocharger component that is as important as the piece parts: quality. Caterpillar and their suppliers go to great lengths to test the quality of turbocharger components and assemblies to see that they conform to Caterpillar specifications. These tests ensure quality is built into each Caterpillar turbocharger. The tests are run on the engine or on a test stand that closely simulates engine operation. These quality tests include 1. Wheel metallurgy. Turbine and compressor wheels are both tested for metallurgical content and processes which might be detrimental to the part's operation. 2. Wheel burst. Turbine and compressor wheels are both tested for the maximum speed at which centrifugal forces cause either wheel to burst. This allows us to set operation limits to avoid these failures on production units. 3. Housing burst containment. Both turbine and compressor housings are tested for their ability to contain wheel bursts. 4. Wheel blade strain. This test is done to assure that turbine or compressor wheel strain levels are low enough to avoid vibration failures in field operation. 5. Wheel and shaft weld joint. This determines the metallurgical soundness of the inertia welded joint between the turbocharger shaft and turbine wheel. 6. Thrust bearing. In this test, the thrust bearing is subjected to high loading by controlling the pressure differential between turbine inlet and compressor outlet. This pressure differential causes high axial loads to be placed on the thrust bearing. 7. Turbine and compressor oil seal. Both seals are tested by applying pressure and vacuum to see if seal leakage can be induced at prescribed operating conditions. 8. Shaft motion. The journal bearings must have sufficient stability to prevent orbital movement of the shaft. If the bearings allow the shaft to move orbitally, metal-to-metal contact would result in premature failure of the bearings or wheel and shaft, and/or both end housings. 9. Bearing housing coking. This test assures a turbocharger has acceptable resistance to carbon formation near the oil drains. Before a turbo design is approved by Caterpillar Engineering, it is run through more than 1,200 cycles to measure carbon buildup. One cycle equals running 6 minutes to attain maximum pressure, then cooling 4 minutes. Even with this thorough quality test program, nothing is designed to last forever, and turbochargers are no exception. Consequently, it is important that our customer has several repair options when service is necessary. It is also important that the customer be made aware of all the repair options offered by our dealership. Various levels of repair might be: 1. Minor repair. This is a before failure option, which normally uses a bearing kit, bearings only, or a repair kit, snap rings and seals. It is a customer's least costly alternative and is based on a preventive maintenance concept. While this option requires more labor than the other alternatives, the savings on parts through reuse make it economical. The combined parts and labor will usually cost 15 to 25% of a new turbocharger. 2. Major repair. This is normally an after-failure repair consisting of new, reused, or salvaged parts. 3. Remanufactured cartridge. These are priced at 60% of the cost of a new cartridge. They can be used to supplement repair capabilities. A cartridge consists of bearings, seals, wheel and shaft, center housing, and compressor wheel. 4. New cartridge. This is the most expensive cartridge repair option and offers little customer value if his cartridge can be repaired at less cost. 5. New turbocharger. This should be used as a last resort repair option due to the added cost. Turbochargers offer high volume profit opportunities for our dealership and also for our engine parts competition, both in terms of new and remanufactured parts and service. Over the last few years, several companies have become actively involved in the turbocharger replacement parts business. So let's look at our 3 main competitors in the turbocharger aftermarket. 1. Rotomaster is a Southern California-based organization committed to growth. Their product line includes turbochargers and replacement parts for on-highway trucks and earth-moving equipment. Their distribution network consists of 92 master distributors and over 1,700 dealers in the U.S. and Canada who supply approximately 225 Caterpillar part numbers. 2. Schweitzer is recognized as a major U.S. competitor for replacement turbochargers and components, new and rebuilt, and related parts for Caterpillar engines. Their distribution network consists of approximately 65 distributors in North America. 3. Air Research's product line includes new and remanufactured turbos and subassemblies, as well as new replacement parts. Common parts are sold through approximately 40 distributors in North America. Besides these three main competitors, there are other smaller companies who offer new parts and rebuilt components for Caterpillar turbochargers. A few of the names you might have heard include Webb Turbos Incorporated, Diversified Turbo Sales Incorporated, Dynamic Diesel Service, and Remans. It is important that you are aware of differences that do exist between Caterpillar original and competitive new or remanufactured turbos and parts. Some differences are visible to the naked eye, like chrome alloy versus cast iron seal rings, and steel bore versus straight bore. Differences not readily visible still exist. There may be differences in tolerances or in metallurgy. The holes and linear voids were visible to the naked eye, but cannot be seen on the slide. For example, Caterpillar recently tested 2 remanufactured wheel and shafts from each of Remanco and Diversified Turbo Sales. A metallurgical inspection showed a chrome-plated shaft with numerous holes and linear voids, which can lead to bearing failure. Also, welded turbine blades looked good, but a fluorescent penetrant inspection revealed serious faults at the weld, which can lead to turbine wheel and turbo failure. A physical inspection revealed, among other faults, turbine blades thinner than original. This indicates that non-current blades may not be suitable for current engine requirements. The above information pertains only to the competitive parts tested. It is not intended to imply that all past, present, or future production of the competitive parts have identical characteristics. But neither the Remanco or the Diversified wheel and shafts would pass Caterpillar quality requirements. These results clearly point out that a less expensive competitive repair alternative is not worth the risk of destroying a turbo or even an engine. Since competitive parts can lead to early failure, it's necessary for the customer to consider ultimate cost when choosing repair alternatives. The customer also receives the assurance of the Caterpillar warranty on original parts. Other less apparent differences involve turbocharger mismatch or misapplication. It is vital that a turbocharger and an engine be properly matched. Different engine systems have varying airflow needs, and these needs must be considered when matching a turbo. Caterpillar knows its engine's requirements, and therefore knows the proper turbo match. A turbocharger that is too large for an engine will operate at inefficient speed and produce inadequate intake manifold pressure. This is called compressor surge. The result is high intake air temperatures and poor engine performance. A turbo that is too small for an engine can cause compressor choke, in which the turbo spins too fast, stressing the unit to the point of destruction. The choke condition exists because not enough air gets into the engine, again causing poor engine performance. As you can see, proper turbo match and application are essential. Even though turbochargers may look alike, there are significant differences. High repair costs can be avoided and good engine performance maintained if our customers stick with original Caterpillar turbochargers and related parts.